All right, guys, so today we are going to just look at one example. We're looking at analyzing a curve. We're going to take everything that we've done in this unit and put it all together. And we're going to look at just one example, but we're going to walk through the steps to analyzing a curve. And I'm hoping that by going through just the one example, you should have a pretty good understanding of how to analyze a curve, or essentially sketch a curve from a formula. So we're going to walk through the steps, and if you're having trouble with any of the points that we're at, you can always go back and review your notes from previous topics. So we have an equation here. It says y equals 2x squared over x squared minus 1. So this is our function. And in order to graph this curve, we're going to have to find out all sorts of things. We'll have to figure out our domain. We'll have to figure out our intercepts and our asymptotes. We'll have to figure out where the graph is increasing and decreasing. We're going to look at concavity. And so all of those pieces put together are going to give us a picture of what this graph is going to look like. So the first thing we do when we are analyzing a curve, or starting with the curve sketching process, is to figure out the domain of our function. And so we're going to start off by looking at our NPVs. So we have x squared minus 1 cannot equal 0. So x squared cannot equal 1. And when we square root, we have x cannot equal plus or minus 1. So that tells us right off the bat that we have some vertical asymptotes at x equals plus or minus 1. And so our domain can be the element of reals, except that it cannot equal x cannot equal plus or minus 1. So if we were to sketch this on a diagram, or sketch this on a number line, okay, we would have restrictions at -1, and we'd have restrictions at +1. And so our domain goes from -infinity to -1, and it goes from -1 to 1, and from 1 to infinity. And if we were writing this using the set notation that we've used before, our domain would go from -infinity to -1, union -1 to 1, union 1 to infinity. So that's where we start off with. We're looking for our domain. And again, by looking for domain, we're essentially looking for our restrictions. All right, once we have our domain, then we're going to get into looking at intercepts. So when we're looking at intercepts, we're looking for both the x and the y-intercepts. And if you remember, an x-intercept, y equals 0, and a y-intercept, x equals 0. So let's start with the x-intercepts. So the x-intercepts, y equals 0. So we've got our function, y equals 2x squared all over x squared minus 1. We set our y equal to 0, and that gives us 2x squared all over x squared minus 1. Now, there's a couple different ways you can do this. You can factor, or we can just multiply out. Because we've already looked at our domain, I'm just going to multiply this over. So 0 times x squared minus 1 equals 0. So 2x squared equals 0. I'm going to divide by 2. And we have x squared equals 0, meaning that x equals 0. So we have an x-intercept at 0, 0. Now, because we looked at domain already, we know that we've lost a point by multiplying 0 times x squared minus 1. But because we know of those 2 points, plus and minus 1, we don't have to worry about them here. So y-intercept, and we also know they're not x-intercepts because they're asymptotes. So y-intercept, x equals 0. So we're going to have y equals 2x squared times x squared minus 1. So y equals 2 times 0 squared all over 0 squared minus 1 equals 0 over -1 equals 0. Well, again, we've got an intercept at 0, 0, which makes sense because our x and our y-intercepts, if the x-intercept's at 0, 0, that would mean the y-intercept is at 0, 0. All right, so we've got our domain, we've got our intercepts. The next thing we're going to look at is asymptotes. And so we're looking at asymptotes, we're looking for vertical, horizontal, and oblique. And it's important to note that we only have to worry about this for rationals. So only have to worry about this for rational functions. If we had a polynomial function, we don't need to worry about asymptotes. So first thing we're going to look for is vertical asymptotes. So we've already looked at this before. We're going to take our denominator, look for our NPVs. X squared minus 1 equals 0. So x equals plus or minus 1. And we're taking that from our domain before. So that means we have a vertical asymptote at x equals 1 and a vertical asymptote at x equals negative 1. Looking for our horizontal asymptotes, we're going to look for the limit of the function as x approaches plus or minus infinity. So 2x squared all over x squared minus 1. And so we're going to have the limit of x as we approach plus or minus infinity. You remember we're dividing by our highest degree. So 2x squared over x squared divided by x squared over x squared minus 1 over x squared gives us 2 over 1 minus 1 over x squared, which is 0. So this became 2, this became 1, and this eliminated to 0. So we're subtracting 0. So we have 2 over 1, which is just 2. And the last one we're going to be looking for is slant asymptotes. And if we take a look here, we've got our function was 2x squared divided by x squared minus 1. So we have a monomial divided by a binomial. There are no slant asymptotes in this case. Had it been reversed, x squared minus 1 over 2x squared, then we would have been looking for slant asymptotes. All right, next thing to look for is symmetry. Is this function odd, even, or neither? And so we're going to test. We're going to do a test point here. We're going to replace x with negative x and see how the function behaves. So first test, we're going to plug this in. We're going to have y equals 2 times, let's write the original function first. So 2x squared all over x squared minus 1. So we're doing our substitution. We're going to have y equals 2 times negative x squared all over negative x squared minus 1. And when we simplify this, negative x squared is just a positive x squared, so 2x squared all over x squared minus 1. If you notice, these functions are identical. So this function here and this function here are the same. And if they're the same, this means they're the same. It means this function is even. And if it's even, it's symmetric or symmetrical, symmetric about the y-axis. Now again, if you remember, if you're looking for odd, we're looking for the f of negative x to equal negative f of x. So for odd, we'd be looking for a different scenario. And if it was odd, it would be symmetric around the origin, symmetric about the origin. All right, so let's take a look at intervals of increase and decrease. So when we're looking at the intervals of increasing, or where the intervals are increasing or decreasing, we want to look at the first derivative, figure out our critical points, and then set up our chart. So we've got y equals 2x squared all over x squared minus 1. Now for our first derivative, we can use the quotient rule. So we're going to have x squared minus 1 times the derivative of 2x squared, which is 4x, minus 2x squared times the derivative of x squared minus 1, which is 2x. And that's all over x squared minus 1 all squared. Now when we multiply this out, we've got 4x cubed minus 4x minus 4x cubed all over x squared minus 1 all squared. Well, our 4x cubes are going to cancel out, and we're going to be left with negative 4x all over x squared minus 1 all squared. Now we're going to set that equal to 0. We set that equal to 0, negative 4x all over x squared minus 1 squared equal to 0. We already know about our asymptotes. So we've got negative 4x equals 0, x equals 0. So we have a critical point at x equals 0, but we also have to consider where our asymptotes are. So we can set this up as a number line, or we can set this up as an interval chart. I'm going to use a number line here. And we'll mark all of our key points. So we have an asymptote at negative 1. So we have an asymptote at negative 1. We have an asymptote at positive 1. And we also have a critical point here at 0. So our intervals are negative infinity to negative 1, negative 1 to 0, 0 to 1, and 1 to infinity. Now, when we're trying to figure out what's happening here, we're going to have to use some test points. And so we're using test points in the derivative. So I'm going to use a test point of negative 2. I'm going to use a test point of negative 0.5. I'm going to use a test point of 0.5. And I'm going to use a test point of 2. Again, we're plugging these into the derivative. So when we plug these in, we're going to find out that this one is positive, meaning it's increasing. This is positive, meaning it's increasing. This is negative, meaning the graph is decreasing. And this is negative, meaning the graph is decreasing. So we have one point here where the graph is increasing and decreasing. So we know that there is likely a maximum right there. So we're looking at a maximum at 0, but we can use a second derivative test to verify that. Okay. All right, so let's get into our local maximum and minimum. So we're looking for relative maxima and minima. We know that we have a maximum at x equals 0. And if we sub in the function f of 0, we'll get that at 0, 0. So our maximum happens at 0, 0. Now we can do this by using the second derivative test, or using the intervals of increase or decrease from before. Okay, so we've taken the 0, we've plugged that into our original function, and we have 0, 0. Now we don't necessarily have to do that substitution again because we did it earlier when we found our intercepts. Now we're going to look at concavity because there might be some points of inflection here, and we're going to use our second derivative test. So our first derivative was negative 4x all over x squared minus 1 squared. And we already know that we have asymptotes at x of plus or minus 1. So let's take a look at the second derivative, and this is the one that usually gets a little messier. So we're going to use the quotient rule again. X squared minus 1 squared. Again, you can use the product rule for this as well, and should get the same answer. But I'm using the quotient rule here. So x squared minus 1 squared times negative 4 minus negative 4x times the derivative of x squared minus 1 all squared. So remember, we're going to have to use the chain rule here. So 2 times x squared minus 1 to the exponent of 1, and then the inside piece is 2x. So it's important that you, when you're doing the derivatives, that you don't forget those inner pieces. So down here we've got x squared minus 1 all squared, and then squared again. Multiplying this through, we're going to have negative 4 times x squared minus 1 all squared plus 16x squared times x squared minus 1 all over x squared minus 1 to the 4th. Now at this point, this is a good opportunity to do some factoring. So we're going to pull out a negative 4. Remember, we always pull out our factor that has the lowest degree. So we're going to pull out an x squared minus 1. And that's going to leave us with an x squared minus 1 minus 4x squared. And if it's helpful to still have this part in brackets, you certainly can, for simplifying purposes. And then in the denominator, we've got x squared minus 1 all to the 4th. So we can do a little bit of canceling here. Top one's going to cancel. We're going to be left with a cubed on the bottom. and we're going to have -4. We've got -4 times inside here, x squared minus 4x squared, so -3x squared minus 1 all over x squared minus 1, all cubed. So we have our vertical asymptotes at plus or minus 1. And we're going to set our derivative, our second derivative, equal to 0 to find our other critical points. So we've got -4 times -3x squared minus 1 all over x squared minus 1 cubed equaling to 0. Again, I'm multiplying that up because we've already dealt with the -1. So we're going to have -4 times -3x squared minus 1 equals 0. Dividing by -4 gives us 0, so -3x squared minus 1 equals 0. So we're going to add 1 and divide by -3. So -3x squared equals +1, divide by -3, and x squared equals -1/3. Now I can't square root a negative, so this tells me I have no points of inflection, okay, because I can't solve that any further. All right, so let's set up our number line. Again, we have a vertical asymptote at -1. And we have another asymptote here at +1. And so our first interval is going from -infinity to -1. This is with regards to our second derivative. Our next interval goes from -1 to 1. And our third interval goes from 1 to infinity. And so again, we can plug in test points here. So I've plugged in similar test points. So -2, 0, and +2. And plugging those in, we're going to get a positive second derivative, a negative second derivative, and a positive second derivative. So when it's positive, that means this is concave up. When it's negative, it means it's concave down. And this is concave up. All right, so we're going to take all of that information and we're going to graph our function. So we know that we have a vertical asymptote at -1, and we know that we have a vertical asymptote at +1. So we're going to start by graphing. And if you had a ruler, you'd be graphing your asymptotes here. So we have a vertical asymptote at x equals -1, and we have a vertical asymptote at x equals +1. We also know that we have a horizontal asymptote. If you go back into your notes, we know that we have a horizontal asymptote at x equals 2. And so you can sketch that as well. I'm just using the graphs to do that. So we have a horizontal asymptote at x equals 2. So, sorry, at y equals 2, not x equals 2. At y equals 2, we have a horizontal asymptote. Now, we know that the graph is concave down, concave up here. And so the graph is looking like this. We know that we have a maximum right here, and we also know that from the second derivative test that said it was concave down. So the graph is approaching, but never crossing those asymptotes. And then we have this other part of the graph here that is also concave up, so it looks something like this. And it should be approaching that line, but never crossing. There we go, something more like that. All right, so if you follow those steps to successful curve sketching, or you follow those steps for curve sketching, which basically takes into account everything we've done throughout this entire unit, you'll be able to take a function and sketch what that graph looks like. All right, guys, now it's time to do a little bit of practice, and we'll see you soon.